Okay, so in the last video we were talking about the covariance matrix, and we started to run out of time, and so I started to write really fast. So let me rephrase this. Let x be n by p, and so we're thinking of that as n, or p points, in Rn. Then mean subtract x, the matrix x, where the mean x bar is in Rn, so that's a column, right? So if you're looking at a matrix X, you're taking the mean across, right? This is n by p. So you would end up with one column, that's your mean. Okay, then you take this column and you subtract it from all the columns of your matrix. Okay, we've seen how to do that in the stats section, chapter 2. Then the covariance matrix, C is n by n, and measures the covariance between dimensions I and j of your data. Okay, and so in computing that, right, we said that C could be computed as 1 over p minus 1 times x transpose. Again, I'm thinking of x as being mean subtracted there. But notice what this is. If you think about, if this is actually, our x is probably going to be a wide matrix if it's n by p, but that's fine. X would be like x1 through xp, right, being columns, and then x transpose would be x1 transpose xp transpose, so those would be columns, right? And so when you go through and measure or compute this, you get x1 transpose plus x2 transpose plus xp transpose. And the thing to remember about this is that these are n by n matrices, right? And so you could write C as 1 over p minus 1 times the sum I equals 1 to p of xi transpose. Okay, so these are two equivalent ways of writing the covariance. Good. All right. So looking at this definition of the covariance matrix, C is n by n and symmetric. So therefore, what nice theorem applies to symmetric matrices? The spectral theorem. The spectral theorem applies. Therefore, we can write C as P maybe times D times P transpose. And we remember how this works in the spectral theorem. The columns of P are they're orthogonal, but we'll go ahead and normalize them. So P has orthonormal columns. I guess I'm just missing the U there. And then D is diagonal with the lambdas along the diagonal. Okay. By the way, what are the diagonal elements of C itself? The diagonal elements of C itself will be the variance in each dimension. So that would be like the variance of the first row, and then in the first of the 1-1 position. 2-2 position would be the variance of the second row. 3-3 would be the variance in the third row, and so on. Okay, good. That actually comes out in the lambdas. The lambdas are the variance in the direction of the eigenvectors, but we're going to talk about that in just a second. I don't want to get too far ahead of myself. Okay, So let's convert this to the SVD of x, right? So gosh, my writing crooked? There we go. Let x be u sigma v transpose. I'm going to let this be the reduced SVD. So therefore, what are sizes of things? U is n by k, sigma k by k. V itself is going to be p by k, right? And so what will C look like in terms of U sigma and V transpose? So then C would be 1 over p minus 1 times x transpose. Now remember, when you take the transpose, we got to write that in reverse order. Why didn't I take sigma transpose? Because sigma is a diagonal matrix, so it doesn't matter if it's transposed or not. Good. And let's simplify this. What do we get here? We get that C is 1 over p minus 1 times U. V transpose V is the identity matrix. And then we have sigma squared. Do you remember how to square a diagonal matrix? If I take d squared, for example, that would just be lambda 1 squared through lambda n squared. You just square the diagonal elements. U transpose. Good. And that is equal to U times 1 over p minus 1 sigma squared times U transpose. Now compare this to this, and you see that the matrix U here, these are the eigenvectors of C, of the covariance matrix, even though we started by saying what? It's the left singular vectors of x. And similarly, what are the eigenvalues of C? Lambda I is equal to 1 over p minus 1 times sigma I squared, right? Where this is the singular value of x. And lambda is the eigenvalue of the covariance matrix. Good. And so you get two relationships coming out of that right off the bat. Right? So that makes it easier actually to compute the eigenvalues of the covariance, because like I said before, we don't want to actually compute XX transpose on the computer because there's going to be a lot of error. Rather, it would be better to take the SVD of X itself, and then you get the you get the eigenvalues, you get the eigenvectors of C, and then the eigenvalues you can compute through the singular values of X. Good. You actually don't need the V in this case, but we're going to actually find a use for V later. Okay, so there will be a use for V. Good. And so that is the relationship between the SVD of X and the eigenvectors and eigenvalues of the covariance matrix. Good. Pause for a second. Good. So what I wanted to do in the minute or two left of this video is I wanted to talk about projections versus the mean. Projections and the mean. So suppose I've got a bunch of data, x1 through xp, and my data is in Rn, for example. Okay, and suppose that I've got a vector u. Let u be in Rn. Okay, then I'm thinking about what is the variance, or maybe I should start off with the mean. What is the mean of the projected data? So just in terms of a picture, right? If this is my vector u here, and I've got my data up here, and I project all the data down, right? Then I want to take the mean of this data. But do I want to take the mean of the data in R2, or do I want to take the mean of the data in R1? Right, because we said in the first video that if these are our xi's, right, and this is my vector u, then I want to treat this as if it were a scalar value along the vector, right? And so the data set I'm going to be working with are the coordinates of my data. So x1, or maybe I'll say u transpose x1, u transpose x2, up to u transpose xp. So these are the scalar projections of the data onto u. And so these are, again, scalars. I want to emphasize that, right? Scalars. U is a vector in Rn, xp is a vector in Rn, but the dot product is a scalar. Good. Okay, so what happens when I take the mean of that data? K equals 1 to p of u transpose xi. Well, the u transpose can be factored out of the expression. And what is this? This is going to be the mean of the original data in R2, right? And so what's happening is you're projecting the mean. This is u transpose x bar. So what does that mean? Theorem. The mean of u transpose xi, I'll be kind of sloppy there, is equal to the mean of u transpose times x bar. So the mean of the projection is the projection of the mean. The mean of the projection is the projection of the mean. Very good. And so the reason this is kind of important is because we're also going to get a similar formula for the variance. But we'll wait for the next video for that. So next video, how does the projection to u change the variance of the data? Right, because originally you've got some variance in your data, and if you do a projection, you're going to get a different variance. We'll talk about that next.